For decades, isolating applications meant using a virtual machine. Think of a VM as a heavy, monolithic metallic box, providing secure isolation, but incredibly rigid. The critical flaw of this approach lies inside that box. Every single virtual machine requires its own entirely independent operating system to function. This creates a massive waste of resources. To run 10 applications, you are forced to boot up 10 full copies of Windows or Linux, burning CPU and memory just to keep those redundant background processes alive. While VMs successfully keep software separated, their heavyweight nature makes them far too slow and resource-hungry for the speed required by modern computing. Containers arrived as the lightweight alternative. They offer the same isolation as a VM, but they launch in milliseconds because they lack that massive OS overhead. To understand this efficiency, we must stop looking at the individual application and zoom out to the node view, the host machine itself. This perspective raises a difficult question. How do we run dozens of isolated applications on one server without them crashing into each other if they don't have their own operating systems? The answer lies in a different architecture entirely. Container efficiency comes from abandoning the concept of individual operating systems and sharing the resources of the host. We start with the node. This is the physical server or foundational virtual machine that runs a standard Linux operating system, like Ubuntu or Red Hat. At the base is the hardware layer, and directly above sits the orange band, the shared Linux kernel. This unified kernel makes containers incredibly fast. Every container sends its core instructions, system calls, directly to this one shared kernel. Because they share the host's kernel, containers skip the time-consuming process of booting a new OS. They simply use the core that's already running, saving massive computational overhead. This shared kernel model enables near-native hardware performance, but it also creates a massive management and traffic control challenge for the system. To keep the node organized, Kubernetes uses two managers that sit directly on top of the host operating system. The Kubelet is the on-site foreman, constantly communicating with the Kubernetes Control Plane to see which application should run. Then, the container runtime, the mechanic, takes orders from the kubelet to build the isolated spaces where code lives. In this relationship, the kubelet is the brain enforcing the desired state, while the runtime provides the muscle required for low-level execution. Without these two managers working in tandem, it would be impossible to safely coordinate multiple workloads sharing a single kernel. To understand what is actually being managed, we look at the lifecycle of the code. It starts as a container image. An image is a static, read-only snapshot of the application. It's like a recipe book. It contains every instruction needed to run the app, but it cannot be changed once it is built. Executed by the runtime, that recipe becomes a live container, the active process consuming CPU and RAM, like a baked cake. Kubernetes then wraps that container in a pod, adding a protective cover and IP address for cluster scheduling. This creates a clear pipeline. Developers build static images, runtimes execute them as containers, and Kubernetes manages encapsulated pods. If pod A and pod B are sitting on the exact same kernel, we have to ensure they don't interfere with one another. Separation is maintained by two Linux features located just above the kernel, namespaces and cgroups. Namespaces provide privacy by restricting what the pod can see. Pod A thinks it is the only thing running on the machine. Cgroups, or control groups, act as the budget, setting strict limits on how much CPU or RAM a pod is allowed to use. These features ensure that even though the hardware resources are shared, the applications remain functionally independent and cannot crash their neighbors. By combining namespaces for privacy and cgroups for resource management, the shared kernel architecture becomes both highly efficient and safe for enterprise production. This is the completed architecture, a fleet of isolated pods born from static images and orchestrated by strict managers. The fundamental takeaway remains that containers are not virtual machines. They do not possess their own operating systems. All this engineering allows hundreds of applications to safely share a single operating system heartbeat, utilizing hardware with near-native efficiency. Mastering this balance between shared underlying resources and strict application isolation is what enables the high-density scaling of modern cloud computing. Kubernetes constricts highly efficient micro-universes atop a single piece of bare metal, turning a lone Linux kernel into a massive distributed engine.